Justin Miller, Rockstar College Physics here, and we are going to look at a couple of nice little problems involving some capacitors, first in a parallel and then in series, and then we move on from there and discover some more things about capacitors, capacitance, and different types of configurations, compound configurations. But let's start with this. Let's do a couple of nice little problems, and let us just start here. So here's the problems. All right, we got ourselves two capacitors, C1 and C2. We'll give them some capacitances. We're going to go ahead and stick them in parallel, connect them to a 15-volt source potential, and then ask, hey, what's the equivalent capacitance? What's the charge stored and potential difference across the plates of each capacitor? And what's the total energy stored? Seems pretty easy. And we'll do the same thing for series. All right, so we're going to take C1 is equal to, let's make it 100 microfarads. Take a C2 and say that it's 200 microfarads. We're going to take a source potential here and say that it's 15 volts. And then first, we'll look at a parallel configuration. So we'll go ahead and take our source potential here, take a C1, take a C2, connect them together in this nice parallel configuration. Got a C1, got a C2, got our source potential, and first off, we want to know what's CEQ. CEQ. Well, if they are in parallel, then they just add straight across, which is really, really nice and convenient for parallel. CEQ is just C1 plus C2, which will then be equal to 300 microfarads. Super simple, right? All right, part B, we want to know what is the charge stored and the potential difference across the plates of each capacitor. So part B, we want to know a delta V1 is equal to, a delta V2 is equal to, a Q1 is equal to, and a Q2 is equal to. Those are all the things that we want to know. And what do we know since these capacitors are in parallel? The potential difference across the plates has to be the same. We must have, because of parallel, that delta V1 is equal to delta V2. All right, so again, if we go back to this equivalent system here, and said, oh, we've got a CEQ there, and we've got our source potential there, and we note that the potential difference, we note that the capacitance of CEQ is just 300 microfarads. What would be the potential difference across these plates? Yeah, that'd be it. We'd have ourselves that CEQ would be defined as Q total divided by the source potential. So that's great. What does that mean? Well, it means that the potential difference across the plates of this capacitor would be equal to that of the source potential. These both directly trace back to the positive and negative terminals of the battery. Thus, these have to also be equal to that of the source potential. So the potential difference across the individual plates of those individual capacitors is 15 volts, just like the source. So that was pretty straightforward there, right? Well, now we also want to get what are the charges stored by these individual capacitors. And for that, we merely need to go to the individual definitions of these individual capacitors. C1 is going to be defined by Q1 divided by delta V1, and C2 is going to be defined by Q2 divided by delta V2. There we go. Charge is separated, or charge is stored, divided by the potential differences, defines the capacitances of the individual capacitors. We know what delta V1, delta V2 are, we know what C1 and C2 are, but boom, guess what? We go ahead and solve this for Q1 and Q2. So this one gives us that Q1 is going to be equal to C1 delta V1, which will be equal to 100 microfarads multiplied by 15 volts. 100 times 10 to the negative 6. Get 15 times 10 to the negative 4 coulombs. or 1.5 times 10 to the negative 5 coulombs, that would be fine as well. 5 times 10 to the negative 5 coulombs. There's the amount of charge stored on a capacitor number 1. And then we go ahead and say, well, what about capacitor number 2? It's going to be gotten by C2 delta V2, which will be equal then to 200 microfarads times 15 volts, which 3.0 times 10 to the negative 5 coulombs. And there we go. We've got those individual charges stored, and that's pretty much that. Sure, I'm messing up some decimal places there. So there we go. Got the charges stored by the individual capacitors. What would be the charge stored by this one? 4.5 times 10 to the negative 5. If I went ahead and solved it out, even though we're not asked for it, we'd have the Q total would have to be equal to CEQ times the source potential. Come on, scripty. And what do we have? 300 microfarads multiplied by 15 volts would be equal to 4.5 times 10 to the negative 5 coulombs. Which consequently is equal to Q1 plus Q2, because that's how things work in parallel, right? There we go. So moving on to this last part, sweeping on over here, part C, we want to know what's the total energy stored by this configuration. U total is equal to, yes, U1 plus U2. That would be fine. We could go ahead and utilize the individual capacitances of the individual capacitors and the potential difference across the plates, add those together. We can go ahead and say that this is 1/2 C1 delta V1 quantity squared plus 1/2 C2 times delta V2 quantity squared. But again, C1 plus C2 is the equivalent capacitance, and it should be easy to recognize that this is going to be CEQ times E squared. Same thing, because these potential differences are that potential difference. So in the end, we've got that this is equal to 1/2 times 300 microfarads, 300 times 10 to the negative 6, multiplied by 15 volts quantity squared. 15 times 15, we got 2.225, something like that. 150 times 15 squared. That's right, it's cubed then. So, oops, 6 times 15 squared. 3.375 times 10 to the negative 2. 3.375 times 10 to the negative 2 joules. And there's the energy stored. All right. So what are we going to do now? Well, we've answered all the questions for those two capacitors when they're stuck in parallel. Now we want to do it if we stick them in series. So now, C1 and C2 in series. Same questions here. So we'll just go ahead and draw this out. We've got a C1 connected directly with C2 along the same branch, and then connected to our source potential. Same capacitors, same source potential, boom. What do we got? Well, part A again, we want to know what is CEQ. How do we figure out the equivalent capacitance of a system that involves capacitors that are in series? Well, this is the inverse of the sum of the inverses. So we've got two capacitors, so we'll have 1 divided by C1 plus 1 divided by C2 quantity to the negative 1, which will then be equal to 1 divided by 100 microfarads plus 1 divided by 200 microfarads to the negative 1, be 66.7 microfarads. Let's make sure here. 1 divided by 100 using negative 6, plus 1 divided by 200 using negative 6, so negative 1, 66.7 microfarads, well, let's just call it that. 6.667 times 10 to the negative 5 farads, or 66.7 microfarads. Either one's fine. This is a nice condensed version, 66.7, that works. All right, so we've got ourselves the equivalent capacitance. Now I want to answer what's delta V1, delta V2, Q1, and Q2. So let's take a look at that. Delta V's and Q's. So, are the potential differences the same? Can we just say the potential differences are both 15 volts? And the answer is definitely not. They're in series. The potential difference across this whole section here is equal to delta V total is equal to the source potential. Wow. Script D problem. But that gets split up, right? We've got a delta V1 and a delta V2. Delta V1, delta V2. And we can't just say, well, that it has to be 7.5 and 7.5, because that doesn't make sense, and that would just be way too easy to go ahead and start saying, no, it just gets split up evenly. So what then? Well, what do we know about this system? Yeah, the potential differences get split up, and the charges stored or separated are the same, because really it's just these two outer plates that store the overall charge separation. The interior plates undergo a little polarization to match the equal and opposite charges on the outer plates. So we know this, Q1 has to be equal to Q2. So do we know what those are? And the answer is, no we do not. No we do not, but we need to be able to figure it out. We should note that if we take this system and go ahead and reduce it down to one singular capacitor, CEQ, again, we'd have that CEQ is defined by Q total divided by the source potential. There we go. So could we figure out what Q total is? And the answer is yeah, of course we could. We've got ourselves that Q total would be equal to CEQ multiplied by the source potential, which would then be 66.7 microfarads times 15 volts, which would give us Q total. Then the answer is, the question is, excuse me, let's ask questions first. The question becomes, well, is that related to Q1 and Q2 in any way, shape, or form that we can utilize? And the answer is, yeah. What happens if we just took these two outer plates and said that those are those right there? What's in between is irrelevant, in a sense. So whatever the charge stored on this equivalent system is the same as the charge stored overall on these two. And it's just the overall charge that gets mirrored across the two individuals. So, as we looked at before, Q1 has to be equal to Q2 and traces back to this, the equivalent system itself, and thus is equal to Q total. So what's Q total? That is just going to be, once again, our 66.7 microfarads multiplied by 15 volts. Which gives us 001. Well, we'll take it. 615. 0.001 coulombs of charge. I want to make sure I'm not sticking something in here wrong. That's it. Cool. So, boom, we got ourselves 0.001, or we could say 1 millicoulomb. That would be fine too. Or 100, 3, 4, 5, 6, 100 microcoulombs. That would be fine too. It's over 3 places. What's that mean? 2, 3,000 microcoulombs. Let's just do 0.001 coulombs. That sounds fun. All right, so we got this nice charge separated And we go ahead and say, well, what about the potential differences? So the potential differences should be pretty easy to get because once again, we can go back to the individual definitions of the individual capacitors. We've got that C1 is defined as Q1 over delta V1. Thus, delta V1 is equal to Q1 divided by C1, which is 0.001 coulombs divided by 100 microfarads. I'm sure to mess that up. 0.001 divided by 100 to the negative 6. 10. 10.0 volts. All right, that's the potential difference across this capacitor C1. Do the same thing for C2. Q2 over delta V2, which gives us delta V2 is equal to Q2 divided by C2, which is equal to 0.001 coulombs divided by 200 microfarads, which would then be 5.00 volts. Or we could have just noticed that, hey, the total potential difference has to be 15 volts. 15 minus 10 is 5, 5 plus 10 is 15, however you want to look at it. It all matches up with what we should expect. So there are the potential differences, that's how it gets split up. The bulk of the potential difference is actually across the smaller capacitance capacitor. All right, what else then? Well, we got the last thing to look at, and that's the total energy stored. U total, which again is the sum of the individuals. Let's just write this out. This is 1/2 C1 delta V1 squared plus 1/2 C2 delta V2 squared. Well, that would be a fine way of writing things out. But what do we know about this? Well, we know that the equivalent capacitance is going to be the energy stored by the equivalent system is going to be 1/2 CEQ times the source potential squared. Are those two really equal? It's pretty easy to see with the parallel case, but with the series case, not so easy to see unless we rewrite things a little bit. So note something here. We could rewrite, say, delta V in terms of Q's and C's, right? So if I say, well, what's delta V1 squared? I can say that that's Q1 squared divided by C1 squared. And I can rewrite this as being equal to 1/2 Q1 squared divided by C1 plus 1/2 Q2 squared divided by C2. And again, just going back to the definition, here we go. So, what do we have with this? Well, look at this. This is equal to 1/2. Q1 is equal to Q2 is equal to Q total. So we can actually factor that out. Factor out the 1/2 on the other side. We've got 1/2 multiplied by 1 over C1 plus 1 over C2 multiplied by Q total squared. And what's the equivalent capacitance of the system? That's right. Inverses. So if we wrote this out, we could write this as U total is equal to 1/2 times 1 over CEQ, which would be that right there, times Q total squared. And what could we do then? Well, if we could go back and we could say, well, CEQ or Q total, we could rewrite in terms of delta V and CEQ. We can write it over here, Q total CEQ times the source potential. So getting that, we can write this just as well as plus 1/2 CEQ times some squared. The big point here is that this right here is the same as this right here. That's it. And that's what we said needed to be the case. Didn't show it for the second casing series, but show it in this problem here. So in the end, what is the total energy stored? Well, it's much easier to go ahead and say that U total is equal to 1/2 CEQ times the source potential squared, which is then 1/2 multiplied by 6.67 times 10 to the -5 farads multiplied by 15 volts quantity squared. Which one's going to store more energy? Which system? The parallel case or the series case? Hopefully you say, well, it's going to be the parallel case because we increased the overall capacitance of the system by placing those two capacitors in series, in parallel. Whereas with the series case, we decreased the overall capacitance. CEQ 6.667 times 10 to the -5. There is 300 microfarads. 66.7 microfarads. Anyways, go ahead and compute this out. We've got 0.5 times 6.667 -5 times 15 squared. 0.00750. And we'll say 7.50 to the -3. 7.50 times 10 to the -3 joules of energy stored, which is less than this, right? By a pretty decent amount. Quite a bit less. Anyways, that's what we've got. Series, parallel, and continue on from there. Next thing that we're going to do is start to say, hey, what if we have series and parallel together? Then what? That's coming in a whole another video. So stay tuned for that, and see you next time. Be well.